Good morning. In this video, I'm going to explain how we can integrate a fraction of polynomials where the denominator is a product between a linear factor and a second degree polynomial. Now, first of all, this is what we call a proper fraction because the degree of the numerator is strictly less than the degree of the denominator. Here, the degree of the numerator is 1, and the degree of the denominator, if we expand it, it's going to be 3. So this is called a proper fraction. First of all, we should decompose this proper fraction into partial fractions, which are much easier and possible to integrate. So the fraction of polynomial is x over x minus 2 factor of x squared plus 1 is decomposed into a over x minus 2 plus bx plus c over x squared minus 1. Now, x squared minus 1 doesn't have roots, real roots. So it could not be simplified or factorized. So it has to remain as x squared plus 1. Now, if it was x squared minus 1, we should write it as x minus 1 factor of x plus 1. So when we can simplify, we should simplify. Or when we can factorize, we should factorize. But here, it remains x squared plus 1. Now, the partial fraction that has a denominator x squared plus 1 would have a numerator a first degree polynomial, because always in a partial fraction, the degree of the numerator should be 1 degree less than the degree of the denominator. So here it's 2, so the numerator should be of degree 1. Here it's of degree 1, so the numerator should be a constant of degree 0. Now, what we can do here, we should find A, B, and C. A can be found by the cover-up method. B and C cannot be found by the cover-up method. They can be found by identification, or there are other methods than identification in order to find B and C. What I'm going to do is I'm going to find A by the cover-up method, and I'm going to find B and C by identifying with x when I do a common denominator. But let's start with A. So the cover-up method, what we do is that we look at the partial fraction of A at the denominator. The denominator is x minus 2, so we cover it in the left-hand side, or we delete it, and we replace in what remains here. In what remains, we replace x, by 2, because 2, it's the number that makes x minus 2 0. So I'm going to get 2 over 5. So A is going to be 2 over 5. Now I have another video detailing the cover-up method that you can watch if you want more details about the cover-up method. So A is 2 over 5, so I get 2 over 5 over x minus 2 plus bx plus c over x squared plus 1. Now B and C, we have to find them by identification, which means I do a common denominator here, which is x minus 2 factor of x plus 2, and the numerator would be 2 over x multiplied by x squared plus 1 plus bx plus c factor of x minus 2. And so we expand the numerator, we get 2 over 5x squared plus 2 over 5 plus bx squared minus 2b plus cx minus 2c. Then we take x squared into factor. We have 2 over 5 plus b factor of x squared. Then we take x into factor. We have minus 2b plus c, or c minus 2b, it's the same, factor of x, and the constants alone, which are 2 over 5 minus 2c. Now, the numerator that I got here, I should compare it with x, because at the end, these two fractions are equal. So the numerator should be equal to x. This means that the coefficients of x squared would be 0 because I'm comparing it with x. So we have 0x squared. So the coefficients of x squared are equal to 0, which means b plus 2 over 5 is equal to 0, which means b is minus 2 over 5. Then the coefficients of x, which are c minus 2b, should be equal to 1 because we are comparing again with x. So it's 0x squared plus 1x plus 0. So I'm comparing with x, or I'm identifying with x. So c minus 2b is equal to 1. This would give me that c is equal to 1 over 5. And finally, the constants should be equal to 0 because we do not have any constant in the other polynomial that we are comparing with, which is x. So 2 over 5 minus 2c equal to 0, which is correct because if we replace c here by 1 over 5, we get 2 over 5 minus 2 multiplied by 1 over 5, which is 2 over 5. So it's equal to 0. So it is correct. This is just to make sure that our work done up till now is correct. So now we have A, B, and C, and we can write the integral as 2 over 5 over x minus 2 plus minus 2 over 5x, which is here B, plus 1 over 5, which is C over x squared plus 1. Now, what I'm going to do is I'm going to write it as 2 over 5 integral 1 over x minus 2, which is this one here. Then this fraction, I'm going to split it into two fractions. The first one, it's minus 2 over 5x over x squared plus 1. So I can write the integral as minus 2 over 5 integral of x over x squared plus 1. And the other fraction is going to be 1 over 5 over x squared plus 1. So I can write plus 1 over 5 integral of 1 over x squared plus 1. Now, the integral of 1 over x minus 2, it has the form u prime over u because the derivative of x minus 2 is 1. So it's going to be ln absolute value of x minus 2. The integral of 1 over x squared plus 1, it's tangent inverse x because the derivative of tangent inverse is 1 over 1 plus x squared, which leaves that we need to integrate x over x squared plus 1. Now, if we say that x squared plus 1 is u, its derivative is 2x. So we need 2 at the numerator. So if we multiply the numerator at 2 by 2, we should multiply by half also. It's as if I'm multiplying by 1. So when we put 2 inside the integral, we should put half outside the integral. So now I have the form integral of u prime over u, which is ln absolute value of u. And don't forget that I have half here. So finally, I will get 2 over 5 ln absolute value of x minus 2 minus 1 over 5, because I can simplify by 2 here, minus 1 over 5 ln x squared plus 1. I didn't put an absolute value here because x squared plus 1 is positive, plus 1 over 5 tangent inverse x plus c. Don't forget to hit the like button if you like this video, and do not forget to subscribe. Thank you for watching.